Welcome to Equilibrium Lecture A. If you leave a closed, partially filled bottle of water in the sunlight, before long you will observe water droplets near the top of the bottle and in the neck. How'd they get there? As the sun shines on the bottle, water begins to evaporate. As the number of vapor molecules increases, so does the chance that they will interact with each other and recondense to form water. This is how water droplets get to the top of the bottle. Changing phase is a reversible process. In a closed container, as the amount of vapor increases and the amount of liquid decreases, the rate of condensation and the rate of vaporization decreases. Eventually, the two rates become equal. When the rate of vaporization is equal to the rate of condensation, the amount of vapor and the amount of liquid stops changing. This is called equilibrium. Just because the rate of vaporization and condensation is equal at equilibrium, it does not mean the amount of vapor and the amount of liquid is equal. For example, the amount of gas at equilibrium will be greater at a high temperature than at a low temperature. There are other kinds of equilibrium besides phase equilibrium. Some chemical reactions are reversible and reach equilibrium too. When undissolved solid sits at the bottom of a saturated solution, there is solution equilibrium. It might look like the same undissolved solid at the bottom of the container the entire time, but the dissolved material comes out of solution and new material dissolves continuously. Only the amount of undissolved material remains the same. This is often referred to as dynamic equilibrium because there's constant activity even though there is no real change. So what we can imagine is you can see this graph here, and of course we have time. And as we said before, you've got the beginning of time. What do we have at the beginning of time? Of course we have the reactants. And then at the end of time, you'll see what we have is the products. But what you'll see here is that our forward rate, and now we need to talk about our reverse rate. So as I see, reactants can go to make products, and of course then what we would consider to be products can then go back to make reactants. So initially what we can see is our reactant concentration for the forward reaction is very high. And as reactants go to start to form products, we know that the concentration of the products is going to go up. Initially, we have no products. So you can see that our reverse rate, to make we have to make some of the products first. So you can see that initially our reverse rate starts off with 0 products, but then our products can then go back and regenerate those reactants. And so what you'll see is at some point in time, you'll see that our rate of our forward reaction, because our y-axis is reaction rate, equals the rate of our reverse reaction, and we get equilibrium right there. And again, you've got to be really careful with that word equilibrium. What is equal are the rates. The rate of the forward reaction equals the rate of the reverse reaction. What happens with the concentrations, however, the concentrations stay constant. So to recap here, we know that at equilibrium, rates are equal and concentrations are constant. And that's why you'll see we get that little flat line there for equilibrium right there. Just stays constant. So if I have 2 bottles of soda sitting in a refrigerator, one is almost full, the other one's almost empty, what I can see is that, of course, I know very well, slowly the sodas are going flat. And this is because the dissolved carbon dioxide is coming out of solution and going into the airspace above. Remember, when gases, they don't precipitate, but when they go out of solution, they rise up, and that's called effervescence. So, of course, there's our carbon dioxide going up into that airspace. Of course, if you keep the bottle closed tightly, the soda doesn't go flat as fast. If the gas can't escape, it soon reaches equilibrium with the solution below. But are all equilibria the same? Does the almost empty bottle retain as much carbonation as the almost full bottle? The soda with the larger airspace has more room for the carbon dioxide gas to spread out. Remember, to stay dissolved, gases have to be contained. As a result, the gas particles are under lower pressure and have a lower concentration. This makes it easier for them to come out of solution. When the almost empty bottle reaches equilibrium, it will have more carbon dioxide in the space above the liquid and less carbon dioxide dissolved than the almost full bottle does. It will be flat. Equilibrium does not mean equal amounts of reactants and products. It means the reactants are turning into products at the same rate that the products are turning back to reactants. Many factors influence equilibrium, including temperature, pressure, and concentration, which we will get into in Lecture B. But you heard me mention various types of equilibrium. We have solution equilibrium. If I have a solution equilibrium, I will tell you that we have a saturated solution. And that's where I started off today's scenario. Making a saturated solution is the easiest thing in the world for me. I grab some water, I dump a whole bunch of solid in it, and stir it up. And if it all doesn't dissolve, I know I have a saturated solution because the maximum amount did dissolve, but then there's excess at the bottom. And so what happens is, in solution equilibrium, say for example, I have sodium chloride. Sodium chloride as a solid, I know I can put it in water, and as we very well know, the ions will dissociate. And I'll get aqueous sodium ions and I'll get aqueous chloride ions. However, if I have a saturated solution, that is an equilibrium solution. So my forward reaction is, in essence, it's dissolving. So I will see that my rate of dissolving is going to equal my rate of recrystallization. And that's what happens in a saturated solution. So our rate of dissolving is the forward and recrystallization is the reverse. If I consider phase equilibrium, anytime I'm at melting point, freezing point, boiling point, or condensation point, for lack of a better word, I am going to experience phase equilibrium. So say, for example, I am at melting point. If I've got some ice here, ice will melt. And if I am at 0 degrees Celsius, if I'm at 0 degrees Celsius or 273 Kelvin, what do I know? I'm at melting point. So what's going to happen? I know that melting is going to take place, but guess what? Refreezing is also going to take place. So my rate of my forward reaction equals my rate of my reverse reaction when I'm at that melting point. We could say the same thing for boiling and condensing as well. So what will be new to us? We've seen solutions before. We've talked about saturated solutions before. We've talked about phase changes before. But what will be new to us is chemical equilibrium. I can tell you that there is a chemical process used to make ammonia. You recall ammonia is free of charge in our bases reference table. And because it's covalently bonded, it is naturally a gas. And what am I going to make ammonia from? I'm going to make it from its elements, nitrogen and hydrogen. And if I give it a quick balance here, I can see that I need 2 nitrogens and I need 6 hydrogens. And there's my quick balance right there. I can tell you that this is a chemical process referred to as the Haber process. And what we will find out is that Haber is a scientist who was trying to make ammonia, and he found out that the forward reaction rate can equal the reverse reaction rate. So as fast as he was trying to make his ammonia, it was being undone into hydrogen and nitrogen. And so we will find out tomorrow that we can use the tricks of chemistry in order to push a reaction in a certain direction. And so chemical equilibrium as well, the rate of the forward reaction equals the rate of the reverse reaction. So it would stand to reason we know if our forward reaction is spontaneous, that we would have a negative delta G value. So if our forward reaction is not spontaneous, we know we would have a positive delta G value. So the truth of the matter is as we said, what's going forward is then going in reverse. So it is happening, so we could say it's spontaneous, but it's not because it's also being undone. So it's not negative, it's not positive. Our delta G at equilibrium is going to be equal to 0. What other number is not positive or negative? So let's consider some of those examples that I already discussed. And so here you have it formally written down as notes. We know that we can see in a saturated solution, our rate of dissolving equals the rate of precipitating. So reading this in the forward direction, we're dissolving, and in the reverse reaction, we are precipitating. I also called it recrystallizing. It's the same difference. We can also have phase equilibrium. I used melting point as my previous example, but as you can see here, I can also use boiling point. I can have my rate of boiling equal my rate of condensation when I'm at my boiling point. And so this equilibrium process is going to occur at 100 degrees Celsius or 373 Kelvin. I already discussed with you melting point earlier today. Of course, our rate of melting can equal our rate of freezing if our temperature is at 0 degrees Celsius or 273 Kelvin. So those are solution equilibrium example and a couple of examples of phase equilibrium. So what we can do is once we have a chemical process identified and we realize that it is at equilibrium, we can make what's referred to as an equilibrium expression. This is also referred to very often as a mass action expression. I have absolutely no idea why it's called a mass action expression, nor do I care. But for any given chemical reaction, if A plus B are the reactants and C plus D are the products, and the lowercase letters are the coefficients of the balanced equations. These are our coefficients in our balanced equation. In words, I'm going to tell you, you can set up an equilibrium an equilibrium constant expression by doing the following. Here are the words. You take the product of the concentrations of the products raised to the power of their coefficients. Now, let me break that down. I use the word product twice in two different contexts. The first time when I said the word product, what I meant was multiplication. We multiply these two numbers together. The second time I used the word products, I meant the things on the right-hand side of the equation. So you're like, wait a minute. If products make reactants and reactants make products, how do we keep everybody straight? As the equation is written in an equilibrium expression, the items on the right of the double-headed arrow are going to be the products. So C and D here are going to be the products, regardless. And A and B are going to be the reactants for any sake of argument. So we've got our product of our concentration of our products raised to the power of their coefficient. Notice that C was raised to the L power, D was raised to the M power, over the product of the concentration of the reactants. and they are also raised to the power of their coefficients. And notice again, reactants are A and B, and they are raised to their respective powers of their coefficients. A is raised to the J power, B is raised to the K power. This is referred to as an equilibrium expression. So it can be generically referred to as an equilibrium constant expression, which could be called KEQ. However, we can get into more specialized equilibrium constant expressions as well. If I use concentration in molarity to calculate an equilibrium constant expression, it is called a Kc. Get it? It's using concentration. If I have all gases, their pressures are, in essence, proportional to their concentrations. So if I have all gases and I'm calculating the equilibrium constant with pressure, it's referred to as Kp. I can also have an equilibrium constant expression for a weak acid, and if that's the case, that's called Ka. I can have one for a weak base, that's called Kb. Or I can have one for a saturated solution, which is called Ksp, solubility product constant. We're going to go through all of these at some point in time during this unit. So let's think about what the significance of this K would be. It would make sense that if my products and my reactants were, in essence, equally favored, whatever number I had in the numerator for products, I'd have the same number in the denominator for reactants. And so the number on top of the same number happens to be 1. So if products and reactants are equally favored, K would be 1. However, look at your denominator and look at your numerator. My numerator is products. So if my products are favored, if I am product heavy, I'm going to have a K that is larger than 1. It would make sense. I have a big number divided by a small number. And that would make sense. I get that K greater than 1. Whereas if my reactants are favored, I have a small value for products and a big value for reactants. And so that would give rise to an equilibrium constant expression of less than 1. So now let's expand even further. When we write our equilibrium constant expressions, a pure solid's concentration is, in essence, its density. And what we know is that density is a physical property of a solid, and so therefore it's not dynamic. It doesn't change. We could say the exact same thing for pure liquids. So since their concentrations are not necessarily changeable, they drop out of an equilibrium constant expression completely. However, our gases, we can change their concentration, and aqueous, we can change the molarity by having more solute or less solute. So we can change the concentration of gases in aqueous species, so they do happen to stay behind. So if I consider the equation that you might see pictured here, the equation that you see pictured here is calcium carbonate. That's like limestone or chalk, if you will. And it's a solid. And I can get it to undergo decomposition, and it will produce carbon dioxide gas and calcium oxide as a solid. So if I go to set up an equilibrium constant expression for this, it's like, okay, I'm going to set it equal to K, and I do the product of the concentration of the products. And my equation was balanced as written. So I look at the stuff on the right-hand side, I plug them in, and then I put my reactants on the denominator. Done. However, what's the deal here? What I can see is that calcium carbonate is a solid. Calcium oxide is a solid. So they have no business in an equilibrium constant expression. And so my KEQ or my KC is just simply going to equal the concentration of the carbon dioxide gas. It is the only thing that would stay behind. So as we look, let's try to practice writing an equilibrium constant expression for this substance. I'll pause the video and let everybody have a little practice at it. And if you try not to look down and see the answer, hopefully you will notice that we would have the products go in the numerator. We've got our NO2, and it was raised to the 4th power right here. I multiply it by water. You're like, oh, hold on a minute, whose water is a liquid. However, this isn't liquid water, it is actually steam. It's got that gas symbol right there. So state symbols are definitely going to matter here. So I have my steam raised to that 6th power right there, right next to it. And it is implied by smashing them together like that, that is multiplication. Then my reactants, my NH3 concentration, this guy is a gas. It goes in the denominator as a reactant, and you can see that it's raised to the power of its coefficient, which is 4. And then finally my oxygen gas as well. My oxygen gas is going to be raised to that 7th power, and it stays in our equilibrium constant expression. So sorry about that false alarm about pausing, but now we can pause. What do you think the equilibrium constant expression would be if this reaction were in reverse? So meaning if it went like this, 4 NO2 gases and 6 H2O gases yields 4 NH3 gases and 7 O2 gases. Well, you can probably imagine it just as well as I can. Instead of NH3 and O2 being in the denominator, it would now be in the numerator. And instead of NO2 and H2O being in the numerator, it would now be in the denominator. So what does that mean? If I have K for any given forward reaction, I'm going to have inverse K for the reverse reaction. So if you recall, back in the day, we did Hess's law. And if we reversed the reaction, we flipped the sign of the delta H. And that's simply because heat is an additive property. Remember, when you add it up, you get the total. However, you can see that an equilibrium constant expression is multiplicative and divisitive. So instead of flipping the sign, what do? We invert it. So it's good to know whenever you have a K for reverse, it's going to be the inverse of the K in the forward direction. So that is all I have for Equilibrium Lecture A. I hope you enjoyed it and have a good day.